Mahajan. I'm from VIT Vellore. So I will be talking about physics-informed machine learning or neural network. And I plan my talk at a very basic level. So I request the expert to tolerate the few slides. So just to clear all this AI, ML, we keep hearing about AI, ML, and DL. So the difference we can see from the understand from the Venn diagram. So basically, deep learning is a case where the network is deep. There are multiple layers. Now, why and where we do really machine learning or why we need it? So the basic fundamental thing is that whenever there is a complex relationship between input variable and output, then that complex relationship or a complex pattern you can try to model. For example, the car fuel efficiency that everyone wants good efficiency. So it depends on multiple things like vehicle weight, speed, acceleration, road slope, and engine parameters. So now this is a complex problem. So what we can do is that we can feed a lot of data, a lot of measurements, and make our neural network learn the pattern, and then predict the fuel efficiency for a new model or new design. Similarly, like we know that today it will rain or not, it's a complicated problem, weather problem, and it depends on multiple parameters such as like air temperature, humidity, and multiple things. So typical approach is that one can do this by data-driven approach, as well as one can embed physics of the problem. So today I will talk about like how we can embed physics of a problem and try to predict the value more accurately. And for that, I will be giving multiple examples. So this is the basic workflow. I think everyone is aware that we need a lot of data to train a model. Then out of that available label data, some part we receive for testing, and most of it we feed to the model for training. We train the model, and then later we test with the remaining 20% held out data, that how our model is predicting. All right, so this I think everyone might have seen this diagram before. Like this is like a artificial neuron, and there are some these input features or input parameters which are being fed here, and the weights connecting the neurons they feed the value further, and there is activation function which can be of different type, which will finally predict the output. So here we go, like that, how this is actually done mathematically. A quick slide on this, that finally what we need to do is that we need to calculate the loss. Like for example, if you are decided for a particular problem, there are multiple features. Then these features we feed to the network and then calculate the loss with respect to the label data, then adjust these weights through back propagation. And finally, once the model is settled, we test it with the held out data. So here is like the gradient descent method. Typically how the weights are being adjusted. You can look up at these are the standard techniques. All right, then the famous matrices that all the time we just look for the R square. That if your R square is equal to 1, then you know the model is perfect. If the R square is 0, then the model developed is just predicting the mean. It's no more better than a mean. And if it is negative, then it is even worse than the mean prediction. This is a famous example you might have seen, like handwritten numbers. This is data set is available in public domain. That handwritten numbers, a machine learning algorithm can detect what number it is. So what we do is that we digitize these pixels into say 28 by 28 pixels. If the color is dark, then the value is 1. If the color is light, then the value is 0. And this vector, this 28 into 28, the 784 input vector we can supply, and this can give the probability. The digit is 0 or digit is 9. So the network can learn if the pattern is 1 or 2 or 3 or 4, which is handwritten, which could be complex. But by using a digitized image and by making a pixels of 28 by 28, we can train this network with multiple images, and then finally we can check whether that works or not. All right, so now let's come back to the PINN quickly. Also, what we studied in last 1 year, that is what I will present. So one of my colleague had in VIT had measured data of hyperthermia, that magnetic induction heating in nanoparticles, where alternating magnetic field induces some kind of heating. So this is he had lots of available data. So it's sort of like 154 curves of temperature versus time. So those curves we digitized from the published works, and So here it is like some data set, and typically the temperature versus time look like this. So there are 9 input parameters, like what is the frequency of the magnetic field, the intensity of the magnetic field, and the parameters related to the quantum dot structures. So all these input parameters, so we try to run it. We made a network, and these are the input features. Like the difficult part is like finding out which are the features which are going to influence the output. So once we identified that these are the features, and we supply to the network, and so we ran the data-driven model, and this is how the prediction goes. That with those input 9 features, we could see that almost the predicted value. I mean, it's not so good. I mean, only purely the data-driven model. So so this is called as a parity plot. I mean, maybe most of you have seen this before. That on the y-axis we are plotting the temperature predicted. On the x-axis we have the temperature which is measured, and this y is equal to x is the perfect line, that the prediction is the perfect. But what I mean, since the model is not so good, so it may happen that your predictions are just going away from the straight line. So closer to the straight line, better is the model. So this was just the data-driven model. Now, what happens when you embed the physics? So there was a standard differential equation which gives the temperature as a function of time. So there is this Brownian and Neal relaxation time. So this is the physics equations which is available to us. So what one can do is that one can calculate the loss, which is just the weight factor, I mean, lambda d times some number, some coefficient for the data loss to the physics loss, and also to the initial condition of this problem. And what we can try to do is that we can try to minimize this loss with respect to these coefficients, and these coefficients can be tuned. So once you do that, then naturally the physics is embedded through the residual of this differential equation. The data already, the features and the information was available. And the third, for any differential equation, we know that we need initial conditions or boundary conditions. So that introduced the additional loss. So all these three combined losses we put together, and we try to train the network in the similar fashion as done in a data-driven model. So finally, so the good thing is that finally with the PINN, the physics-informed neural network wins across all the different models. So we got the best prediction for PINN compared to all other data-driven models. So here is the case, like R square. Then now the question arises that how do we tune the lambdas, the weight factors? So then we ran over different combinations of lambdas, and found out that what is the best coefficient, how much weightage to be given to the physics, and how much weightage to be given to the data. So that best combination, one can find it out, and one can come up with the best model with the best prediction. All right, so this is the result, and this was published in IEEE Transactions recently. Uh, and one can see here, I mean, as I was saying that near y is equal to x line, mostly the predictions are close. I mean, this is the best among all models. The next system is completely different. That is tunnel FET. Again, this is like a device, and we try to digitize the data and develop a model, something like this. So in this model, there are some around 11 input parameters, but the entire physics, like the quantum tunneling of say band to band and the trap assisted tunneling, that requires some 18 inputs. Now the problem is that only 11 information, I mean 11 parameters are available, but 7 parameters are not available there. So what one has to do is that use latent parameters, make them also learn to the network through the backpropagation and update. So in this case also, what we found is that the physics informed machine learning does far better than purely data driven case. So mostly whatever the prediction, but like this brings in a new paradigm. Like so far in devices we do TCAD simulations, but if the machine learning model can predict and it is faster, then maybe that future is not very far that we can get all the device simulations through machine learning. The third example which I want to tell you is about this electrospinning. That since I mean Delhi is highly polluted, then me and my student we just decided, okay, let's work on some filters. So we fabricated this nanofiber filters, and tested them for their pressure drop and for their efficiency. So typically, people, in the literature, a lot of works already reported on the diameter prediction. So for example, this diameter can be dependent on the process parameters such as the concentration of the polymer solution or applied voltage or the distance or the injection rate. And thereby this mean diameter of these nanofibers do vary. So this complex relationship between the process parameters and the diameter of the nanofiber again can be learned from a neural network, and this is already being reported. So what we did is the pressure drop prediction, and again we just a simple constraint on the permeability, we could get the model learn very well both this pressure drop and the efficiency, and around 0.98 r square we got for both cases. So the point is that again bringing in the physics improves the model. So this is again published in Results in Engineering, very recent publication. Then we started since last 2 months only, I started working on this 2D materials and the DFT database. So we got one result for that I will present in the remaining time. So now the question is that why machine learning on DFT data? The thing is that there's a vast space. Millions of possible combinations, as the earlier speaker told you, that there could be millions possible combinations of structures, and then DFT is computationally heavy. It can take a lot of time, and ML is very fast, so it can give the answers in milliseconds. Now for that, there are multiple databases which are available in the literature. One is this C2DB, where 16,000 materials are available in the public domain. Jarvis 2D is another data set where even the exfoliation energy is given for these 2D materials. And there are others. So in this work, we will focus on the C2DB data. So what is this data? What they really do is that there are these 2D crystal structure prototypes, and we do they do the decoration with different possible combinations of atoms. So then you get millions of or thousands of combinations of materials. Now this could be good or bad, or may not be thermodynamically stable, or this may not be practically be possible to fabricate. But the thing is that at least they have done a thermodynamical stability analysis, and the ones which are only stable, those have gone into the workflow, and they have created a publicly available database. So this C2DB database we took for the case and tried to study the 2D excitons. So there are different types of excitons in 2D. One is the Vanier and the Frankel. These two type we try to involve. And again, as we did in the previous cases, that for hyperthermia case, that there is a differential equation. Here is also there is an equation. This is called as the Vanier-Mott equation, and we use the Kildice potential for that, and the boundary conditions. So we follow the same procedure, calculate the total loss with these coefficients. Now feed this in the network as a residual. Plus there are some data, which is the data-driven cases, some features such as the band gap, the effective mass, hole effective mass, layer thickness, polarizability. So these are the ones which are fixing the data loss. The other earlier case differential equation is going to give us the physics loss and plus the boundary condition loss. All three combined together, and the model is trained with that. So this is what we got finally. So in the literature for binding energy, mostly the R square reported is around 0.8 and around 0.85, and for the completely unknown data set, even it falls down to 0.2. So this case, when we embed the physics into the model, what we see is that R square does quite well. The prediction is quite well, as you can see in this plot. And now one can come up with some materials where the binding energy could be more than 1 eV, for example, or around 1 eV. You can see that there are these cases for which the binding energy is above. But these were the case for only for TMDCs. So now if, but the C2DB database gives the binding energy for around 300 materials, not only for this. So what we did is that we introduced something called as a GNN. This is again a very popular and very strong method. So the graph neural network, where the actual situation or the geometry is being embedded as nodes and edges of your crystal structure. And there's a message passing that the neighboring atom passes the information to the next atom. And this iteration one can go at the R, for R layers, like neighbors, 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 neighbor. I mean, that's how typically the crystal is, like it is influenced by all the neighbors, right? So this way, this is something called as a message passing. Then once the message passing is over, we do something called as the pulling of the data. We bring out a vector, which will pull all this information together. And this pulled vector along with the other features, one can again do the prediction. So what we saw is that when we incorporated all the 300 materials from the C2DB database, then there are excitons which are not linear type. So Frankel is also mixed. So the differential equation which I showed you earlier, that works for linear but not for Frankel. So in that case, since the GNN was used, we saw that only the pure differential equation, it really fails. It cannot work for all those naturally, because the excitons are of different type. Then when you involve some more parameters, linear physics parameters, then the prediction becomes better. And the full model with this GNN plus the linear equation plus the gap feedback, when everything is applied with around 22 features, that time the model works the best. So in the literature, this value is reported around 0.8. So this is so we got a better model, a better prediction for binding energy. All right. So the same thing can be seen from the parity plot. All right. For the material prediction, I mean, this is the basic standard funnel. So what we can do is that look for the candidate space as it is done for the C2DB. Then go with the thermodynamical stability screen. Then the property which you are looking for, I mean, in this case, I'm looking for the binding energy, or I can look for the lifetime also of the or exfoliation energy, or whatever property. I mean, the procedure is the same. Then, but this is the finally the ML prediction. I mean, this is for the screening. I mean, thousands of materials are there, so ML will give you the quick answer. But we know that the DFT is the gold standard with advanced methods. So finally, when you come down to fewer number, let's say around 100, then again one can do the DFT verification. If the DFT verification is correct, then finally one will. So we plan to get around 10 materials for the experimentalist to fabricate and validate. So this is what is the future plan we worked. Okay, so I would like to thank my team. Amrita, who worked on the hyperthermia problem, Athira worked on the TFET, and Darshini worked on the Vignesh and Darshini worked on the electrospin predictions. So thank you very much.
Thank you.
30.
Hope I'm audible to you.
Yeah, yes, yes, yes.
The mod 1 year is on this side. Here, the remaining is are on the other side.
The positive values.
Yeah.
So I mean the R square can be negative, no? R square value by definition can be negative.
That is the R square value.
Yes. It's a cross-validated R square. I mean, we shuffle the data set and do it for different shuffling case and cross-validate. So R square for the, I mean, purely physics, only linear mode equation, it really fails.
Yeah,
Yes.
there's a question there. Sorry, I missed some part of your report. So, is it possible to predict some information on the thickness dependence of, say, single particle band gap and optical band gap using your model?
Yeah, band gap prediction is possible. I mean, well, let me see if I have.
Dependence on thickness of the material.
Yeah, absolutely. Because
and
that.
How much data do you need for that, the preliminary data?
The experimental data you mean,
Yes,
or the?
because in all these databases, it's only single layer, as I believe, no?
Yeah, so around, so even if you can supply between 100 to 200, that should be good enough.
Okay.
So even for the TMDC, we just did only with 56, I think 54 or 56. So it works. But yeah, if you can supply me around 200, that would be great.
Okay, up to 200 nanometers.
No, I mean data sets.
So data set
Data
of
sets.
the same material or what?
So if you have, let's say, maybe up to 50, it should be fine. I mean,
Okay. Thank you. We
thank
will
you.
talk.
Thank you. Okay. I would like to thank Ashish also. Because of him, I'm here. He only introduced me to QMAT, and this is the first time I'm coming to QMAT and getting to see, getting to hear very good talks.
Any other input?
Okay. Thank you very much.